Or how would you do the conjugate of like e to like the negative x squared over like the sigma of time? So it's basically one e to one over a complex number. The negative x squared over a complex number. Yes, sir. How would you find the complex conjugate? There's a complex conjugate. So it's almost like a, you know how limits, you have a lot of like the transform. Sorry. Not a set rule for that guy. Had to do about the homework in the day, how to take complex conjugate of this part of the wave function. So psi has plus out front, then we have x squared over 4 sigma squared. Sigma is a complex number. I'm going to write this 1 plus I just to make it compact. E tilde, which is e over that tau on naught, make the time scale. So you just to take a complex conjugate. Everywhere a complex number occurs, you take its complex conjugate. So you need to find sigma star. Okay, so if you multiply these together, you have x squared over the exponentials, right? Product of 2 exponentials because the exponential of the sum. Multiply them together. Sigma squared plus 1 over sigma star squared. Are you with me so far? Okay, sir. It's down for you. Okay, so 1 over sigma squared, 1 over sigma naught squared times 1 plus I tilde. And the complex conjugate of that we want to add those two together. So to add 2 complex numbers, it's going to be easier to rationalize it. That is to multiply this by the complex conjugate. So we have 1 over sigma naught squared, 1 over 1 plus I tilde, 1 multiplied by the complex conjugate. This will simplify. Then you multiply that by its complex conjugate, so you get 1 plus squared by its real multiplied by its complex conjugate. And this one is going to be the complex conjugate of that, so it's going to be 1 plus I. Okay, now we add those two together. The imaginary parts cancel. We get this plus this. They have the same numerator, same denominator. Okay, so that's what you get for the argument of the exponential. You got to multiply by negative x squared over 4 still. So that part of the probability is minus x squared over 2 sigma naught squared 1 plus tau tilde 1 plus t tilde squared. Okay, so that looks like a Gaussian with this thing as the sigma squared. So he calls that the sigma squared of the probability. So the probability has a time-dependent width. It's like the wave function, except that this is complex, so it's harder to figure out exactly what that means until you multiply the 2 wave functions together to get a probability. that's how you change the exponential. Okay, so all this detail is in the solution. So study the solution. You still have a question if you study that. You haven't quite gotten it down. It's just be careful about how you handle the complex numbers in the complex functions. Okay. Okay, so I said there were two general types of problems that we would tackle with the Schrodinger equation. Do you remember what those two general types?
Bouncing and scatter.
Not bouncing.
Bound states and scatter.
Bound states and scatter. Bound state problems. Problems. We will be looking, we'll be studying bound states, scatter. Bound states, we've done one example. What was that?
Particle in a box.
Particle in a box. Have that memorized. Those solutions you should memorize. Particle in a box will keep coming back. So particle in a box, we're going to do another one in a little bit, which is a simple harmonic oscillator. Put mass on the end of the spring, or have a restoring force to keep the mass close to the equilibrium point. And that will be, we'll study the quantum simple harmonic oscillator. Right? It's different than the classical problem that we looked at earlier. Another example in 3 dimensions will be the hydrogen atom. There are lots of such problems. So we've done this one. We'll look at those coming. Now we're going to do some scattering problems. And so you might have, for example, a simple problem would be to have a potential energy as a function of x. And you send a particle in with some energy. And it's going to interact with this barrier. Some of the particles in the ensemble, some fraction of the ensemble will reflect, and some will make it through the barrier, even if the energy is below the height of the barrier, for example. This can be quantum tunneling. So we want to, this is what we're going to look at next, is problems like this. Okay, and so we're going to start again with the time-dependent Schrodinger equation, but we're going to look at pure modes. Start off with the time-dependent Schrodinger equation. What's different than what we've done before is we've got this something that's we've done the free particle before, not really a scattering, it's just free. So we're going to solve this problem where V of x is some not flat potential. In this example, I've drawn it. This is a little simpler to draw, simpler to solve because it's piecewise flat. It's flat in regions, but then there's discontinuities between the regions. So we're going to study solutions where this potential looks like this. Okay, so the first thing we're going to do again is to look for pure modes. Okay. So when we write down the pure mode, the time independent Schrodinger equation. Like this. Time dependence has been factored out. The pure mode has a specific time dependence. What is the time dependence for pure mode? That's not time dependence.
Minus omega t.
E to the minus I omega t, right? So this complete wave function here, pure mode, that we're going to factor out we're assuming that all parts of the wave function have one frequency. Maybe it's a special kind of solution. What I haven't proven to you is that we will be able to superimpose pure modes to construct a general solution to the time dependent problem. And so it's a very handy technique because it takes a problem which has time dependence and turns it into one which is purely spatial. Okay, and so we're going to look at this kind of problem. For example, where the potential barrier looks like this. And actually, we're going to do one a little bit simpler than that first. But notice here in this that the energy here is assumed to be finite, and the potential here is assumed to be finite. So that means that the second derivative of the wave function is finite, which means that psi prime, so psi double prime is finite for all x, implies that psi prime of x is continuous for all x. See why? You have a discontinuity in the wave function, then the second derivative would be infinite. You have a function like this, where the slope is discontinuous, then the second derivative, the next derivative of this function will be infinite. Right? A cusp like that has no derivative, right? At the cusp. Okay, and that also implies, and psi prime is continuous and also finite, so that also implies that this is, this also implies that psi is continuous. So when we have a barrier like this, a barrier problem like this, as long as the potential is finite, then we have both the wave function and the first derivative are continuous, and this will help us to construct the solution to recognize that. You see, again, you see why? Because if psi of x is discontinuous, psi prime would be infinite, and psi double prime would also not be defined. So the fact that this is a function, remember this kind of differential equation is a function of x on the left-hand side and a function of x on the right-hand side. And so the function of x here is continuous. And so the second derivative must be continuous. Okay, so I'm going to use that. We're going to solve this problem coming up, but we're actually, before that, we're going to do a little bit easier problem, which is like this, except it's going to change the condition here. So the first one we're actually going to do, the first scattering problem we're going to do, is for delta function. So what does that potential look like?
It'll just be zero everywhere, but it'll be infinite.
Yeah, it'll blow up. Let's see, I need a different color. It's white, that's not going to help much. Better to have this in red. So the potential looks like that. It blows up. It's zero on both sides and flat on both sides. So v of x is zero out here, and v of x is zero over there. Just right here, it becomes infinite. Okay. Now that's going to modify the statement that we just made, that the wave function and its first derivative are continuous everywhere. That's not going to be true anymore, because this potential becomes infinite. It's going to say something about the second derivative must be infinite, exactly at the origin. So the wave function and its first derivative will be continuous except at the origin, where that delta function blows up, because this becomes infinite, so this must become infinite. So let's see how that works. Let's take this equation, and I'm going to integrate. around 0. Oops. Epsilon is some small number. So it's close, you're straddling the origin, just taking a very narrow region around x equal to 0, integrating both sides of this equation. Okay, so if epsilon is really small, then this is going to give you approximately this integral, just this, it's the area under the curve, right? So it's just 2 epsilon, the width, times the value of the wave function at 0. If epsilon is small. So that interval gives something proportional to epsilon, the width. And if I shrink the region down, this is going to be going to 0. The area under the curve from that minus epsilon to plus epsilon, and if epsilon is really small, then the box width is decreasing, the height's not getting any bigger, so the area is going to shrink to 0. So as epsilon approaches 0, this is going to get 0 on the left-hand side. Okay, this must be matched on the right-hand side. How about this one? We're integrating a second derivative.
First derivative.
Pardon?
First derivative.
Yes, the first derivative evaluated at the 2 limits. So it's minus h bar squared over 2m times the first derivative at epsilon minus the first derivative at minus epsilon. Right, that's just the integrating the derivative gives the function, the difference in the function. In this case, the function is the second derivative. So integrating the second derivative gives the difference in the slope on the 2 sides. Okay, in this term, well, the potential is a delta function. So we make this E naught bar times the integral of the delta function. What is that interval? Epsilon is not 0, but it's small. But it's not 0. Should be 1. Should be 1. Exactly. So this is 1. Okay, so here we have the difference in the slopes is not going to be 0 because it's going to be offset by that. So let's write this down. And then we take the limit as epsilon goes to 0. So this is psi prime on the plus side minus psi prime on the negative side plus E naught bar. It says that slope is going to be different on the 2 sides of the delta function. Yes, sir.
In the last integral, in the integral, you still have psi x, right? Delta psi x.
Ah, yes, thank you. Right. Thank you. This gives, thank you very much. I made a mistake. I just copied down the side from here. Okay, so this is remember the delta definition of the delta function is the psi evaluated at 0. Okay, so let's write that down over here. What we have then is that the slope on the right side is different than the slope on the left side. And the difference, the discontinuity in the slope, is proportional to the strength of that delta function. So we're going to write this down as 2m E naught bar over h bar squared times psi evaluated at 0. So in other words, right at the delta function, the wave function is going to be continuous. psi is continuous, but it has a discontinuous slope. And so this is psi of x will look something like this at x equals to 0. We'll have a discontinuous slope because of that delta function. Right? So just before this, I said if the potential is not infinite, then the slope must be continuous everywhere. Psi of x, psi prime of x are continuous everywhere. This escapes that because the potential has become infinite. So where the potential goes infinite, the wave function now has a discontinuous slope. I actually saw that for the particle in the box. Remember the wave function, for example, in the first ground state, looks like this. It's 0 outside the box, and then it goes like the sine. 0 here. See, there's the discontinuous slope is right here and over here. The potential becomes infinite, infinitely stiff wall. And so the wave function is discontinuous. The slope is discontinuous. The wave function is continuous, but the slope is discontinuous. Okay, so this is also going to be true here. Again, where the potential becomes infinite, the slope of the wave function is discontinuous across that infinite potential spike. Okay, so we're going to save this. We're going to use this in constructing the solution to the scattering problem. Hold on to that.
Now we're going back to the scattering problem.
Yeah, we're going to scatter off the delta function. So rather than doing the scattering off of the box barrier, I'm actually going to do scattering off of the delta function. It's actually easier than the box problem. We just had to get this first. But now the rest of it's going to be easy. So here's the problem: scattering off delta function. It's called the delta barrier. So in other words, the particles coming in, the potential is flat. So it's going to be a free particle, but then it hits this infinite force that's happens over a very small distance. So it's kind of hard to construct such a thing, but it's mathematically easy to solve. And then we're going to go to more realistic potentials in the delta function area. Okay, so we're back to this problem. V of x is equal to v naught bar delta of x. Write that in here. Okay, so we're going to have two regions. Barrier is right there at x equals to 0. So we're going to have region 1 and region 2. Region 1 is for negative x and region 2 is for positive x. And we're going to set the problem up in the following way. We've got a defined energy. We're going to have a particle coming in from the left with energy E. So remember, this is an ensemble. What I mean by this is each copy of the ensemble has one particle coming into this energy. Everybody's got different copies, an individual copy. And so this is representing an ensemble. A single particle is coming into the delta barrier. So what we're going to find is there's a probability associated with this. Some members of the ensemble are going to bounce back. Some members are going to make it through. So our task is to find the reflection and transmission probability. So we want to solve the Schrodinger equation for reflection and transmission probability. One parameter parameter here is the energy. Of course, it's also going to depend on the mass and the strength of the delta pair. And that's all going to come into these things. Okay, so having divided it now into two regions, for x less than 0, this is 0. So in region 1, here's the equation. And we're wanting to solve. That's the free particle equation. Solve this, right? Coming in from the left, the potential is flat. So in this region, it's going to be free particle solutions. We've got the energy is defined, and we've looked for solutions to that. And we also know that there's a part here that's going to be coming in from the left, and there's going to be a part bouncing off, headed to the left. Okay, so the wave function in that region is some combination of a piece that's moving to the right. This is the incoming. And this is the reflected wave. Right? This, either one of these terms is the solution to this equation. We have a left traveling wave, a right traveling wave, and a left traveling wave. The right traveling wave is the one we're sending in as part of the setup of the experiment. And then the reflection is what happens when it hits this barrier. Some of it gets reflected, the wave gets reflected. Okay, but for this to be a solution here, we have to have this relationship. Right? Substitute either one of these or both of them into this, gives you this condition between wave number and energy. Right? The energy specified at the setup. So K then is going to be 2m over h bar squared for up to me. Remember, K is like the spatial frequency. It's inversely related to the wavelength or the wave for this particle. Okay, so far? Any questions? Yeah,
Why is A, E, I?
A and B are the amplitudes for the waves. They're complex numbers. A is determined by the experiment. It has to do with how many electrons are coming in. So there's one, right? So A is the strength of the incoming wave. B is the strength of the reflected wave.
I was asking why is it when it's reflected, it's the conjugate of the other side almost. Like
Going the other way.
the E to I, negative I, KX.
That's a left traveling wave, remember?
Direction.
Yeah, this is left traveling. The sign of K here, sign of this piece, determines whether it's right or left traveling.
Why is the potential 0 again?
Yeah, so the potential is not 0, only at x equals to 0. So in this region, the potential is 0. In region 1, x less than 0, B equals 0. Because it's not 0, only exactly at x equals 0. So it's a free particle out here. It's coming in, it's a free particle, but then it hits an infinite force. Some part of it's going to bounce off. That's this left traveling piece. Yes, sir.
For this problem, are we kind of ignoring what's happening at that singular infinite point?
No, we're going to use this to treat what happens right at the origin. So we had to set this up first to figure out what to do about that singular part. And this is what we're going to use. Okay, so there are, in general, for a free particle, left and right traveling waves. The right traveling wave is what's been set in motion by something, source of the electrons. And this is going to be the part that bounces off. We're going to have to find B to get the reflection probability. B over A is going to give us the reflection probability. The fraction of the incoming gets reflected. Okay, so far? All of this is in the book. I'm just walking you through it. You're going to walk through it again as part of your homework. You might want to watch this video again after you read it. And also remember, by the way, for every reading that you have in the chapter, there's usually a section in the summary of the chapter. It's really good for you to go to, after you read something, go read the corresponding part of the summary. It helps you stay above the details and get lost in the details with these things. The summary helps you to keep your perspective about how this fits in with other things we're studying in the chapter. Okay. So don't just read that, only that part in the summary, but read what comes up before too, because that will be reviewed. And you'll see how it connects to the stuff we've done before. Okay, so far? All right. Now let's look at the equation for region 2. We're going to connect them after we get these two solutions. Region 1, region 2, we're going to use this to connect them. So region 2, x is greater than 0, the potential is 0. Over here, after it makes it through the barrier, it's a free particle again. Okay, so it's the same equation. And in general, there are two solutions again. K still has that same relationship. The wave number, there are two pieces possible. This is a right traveling piece. This is a left traveling piece. Okay. So if we're over here and we have a part that's going this way, that's what made it through the barrier. So this is the transmitted piece. Part of the wave function that represents what made it through the barrier. How about that left traveling piece? That would mean that there's something coming from over here. But that can't be. There can't be anything coming from over here because there would have to be something over here that's creating it, pumping it in. But our setup says we've only got electrons coming in from this side. So we set that to 0. This has to be 0 because there's nothing over there that's going to be pumping electrons in. There might be, if there's another barrier over there, then we'd have to have something. But then we would have 3 regions. Right? We'd have this region and the region in between the 2 barriers and another region. Right? So we only got 1 barrier divided into 2 regions. And then we're going to stitch them together here. Okay, so there isn't anything that can give rise to the left traveling wave. So we've only got 3 pieces here. We've got the incoming, the reflected, and the transmitted. And this doesn't fit in to that scenario. The way we set it up, there is no contribution. There's no part of the wave traveling to the left in this region. Okay? All right, and now here we're going to stitch them together. Here it is. Okay, so we have psi 1 of x. Psi 1 of x is continuous. I'm sorry, psi of x is continuous. So psi continuous everywhere. Psi prime is continuous everywhere except across that interface between the 2 regions where the barrier exists. There's a discontinuity in the slope. Okay, so first, psi is continuous everywhere. So these two pieces, the left and the right, have to match at x equals to 0. But the slope is going to be discontinuous. So psi prime plus is in region 2. Psi prime minus is coming in from region 1. So we have psi 2 evaluated at 0 minus psi 1 equal to 2m e naught over h bar squared psi 0, which is matched. Doesn't matter whether you're using 1 or 2. Okay. See how we got here? Take a step back. We started with the Schrodinger equation, but our potential is 0 everywhere except right here. So we divided it into 2 regions. Because in each of those 2 regions, we have just free particles. There's no force acting. We have a piece coming in from the left, and a piece that's bouncing off of the barrier. And then in region 2, we have a piece moving to the right, and no reflected wave there. So we solved the Schrodinger equation in these 2 regions. Very simple solution. And now we're going to apply the conditions, the continuity conditions on the wave function. Wave function itself is continuous across here. So whatever we have coming in from the left and the reflected part is going to match what's going out to the right. It's going to match only at this point. They have to meet each other right here. But there's a discontinuity in the slope. Slope is not going to be the same if you're coming in from the right or coming in from the left. The discontinuity is proportional to that. There's a bar over the V here. Proportional to the strength of the delta function variable. Yes, ma'am.
Why is it not a negative sign for the discontinuity of the slope? Go back to like the original
Did I mess up?
one. I don't know if I'm like dumb.
Let me see. No, I did it right. Yeah. So so that originally comes from integrating the Schrodinger equation. And then there was a negative sign here. And this was 0. When we integrated, we get 0 on the left-hand side. We have this negative sign here, and then we have the v naught psi of 0. And so we bring this over to the right-hand side.
Oh, the
So
negative
this is
sign.
correct.
Okay.
Yeah. Check that in the book. Also, when you're going through it. This is correct. Okay, so far? All right, so these are not differential equations. These are boundary conditions at only one value of x. In other words, these are algebraic, not functions of x. And we've got the solution set in both regions. So we have unknowns. What are the unknowns in the wave function? There are 2 unknowns. A is known because that's part of the setup.
Well, B and C.
B and C are the unknowns. We need to find B and C. We have 2 equations and 2 unknowns. So we can completely solve for the problem of finding the reflected and transmitted pieces. Yes, sir.
Would A to the, or yes, A, would that be equal to B plus C?
Yeah, that's almost. A plus B is equal to C. That first equation? Is that what you're asking?
Yeah.
Yeah, that's right. So let's evaluate. We have the wave function written down here and here. And let's evaluate them at x equals to 0, right at the place where the delta function, where the singularity exists. So this evaluated at x equals to 0 is just A. This evaluated at x equals to 0 is just B. A plus B has to equal C, but this is also evaluates this C at x equals to 0. See how that works? That's the first first condition. Let's call this one A. No, don't call it A. Equation 1, equation 2. Talk about this. So equation 1 just gives that in terms of the two unknowns. B and C are the two unknowns. A is part of the setup. It tells about how much the intensity of the incoming beam. All right, now let's look at that second one. We got to look at the second one. We got to take derivatives. So to get equation 2, take the derivative of this, and then we need to evaluate that at x equals to 0. Okay, so let's look at the derivative. IKA to the IKX. What is the next term?
Minus
Good. And so the derivative, the slope of that is going to be E, it's going to be IK times A minus B. And then with opposite signs, A and B come in with opposite signs. Let's look at the slope in the second region. What's the slope? The derivative. Just got this one piece.
IKC to IKX.
This is 0. Excuse me. Okay. So equation 2 starts off like this: IKA minus B is equal to IKC. Oh, oops, excuse me. Sorry. All right. Minus IKC is equal to, right? Subtract off, I did it backwards. Psi prime in the second region is IKC. And we want to subtract off psi prime from the first region. And then this is going to be equal to 2m b naught bar over h bar squared times psi evaluated at 0, and we can use either a plus b or c, doesn't matter. It's going to be equal to each other. Right, so put in this plus b if you like, or c.
Use C.
Yeah, it's probably easier to use c. Yeah, let's just use c. It's just a little simpler. It shouldn't matter. You do it correctly. Okay, so we have two equations and two unknowns. Remember, B and C are unknown, but they're complex.
A is also complex.
A is in general complex. So we need to solve these two equations for B and C. They will be proportional to A. Both B and C will be proportional to A. Why does that? Why do you suppose that is? Yeah.
Because that's what we're shooting out, that many oracles, so that we can make sense to be proportional.
Right. Yeah, it's going to be proportional to what's coming in. What makes it out is proportional to what comes in. What goes out is either reflected or transmitted. But it all starts as A coming in, so it's all going to be proportional to A. Okay. So that's your homework, is to solve for B and C. See basically how to do it. Yes, ma'am.
So does A plus B equals C? For some reason, it's looking like it violates conservation of mass because you have one thing coming in, and that one thing coming in should equal the two things that come from it, because it's like A splits into either B or C,
But A and B are not mass. What are A, B, and C?
the particles.
Not particles.
Intensity,
Yeah, it's a probability amplitude. Remember that we have a probability amplitude. We're going to take this squared to get a probability density. The wave function is a probability amplitude. The absolute magnitude squared is a probability density. Okay, so your question is close. Is probability conserved? Should be. Everything that comes in should show up somewhere else. Some that comes in is going to be reflected, and some that goes out is going to be transmitted.
so you think that A equals B plus C? That's kind of where my logic is leading.
Yeah, but you're not right about that. Yeah. Right. So we're going to find that this ratio is the transmission amplitude. Whereas the ratio of B to A is the reflection amplitude. But it's an amplitude, not a probability. How do we get a probability from it? Take magnitude squared. So we should have she's exactly right. Our solution should preserve probability, total probability. We're not losing anybody from the ensemble. So everybody's got to show up either in the reflection or the transmission, but as a probability, because that's a fraction of the ensemble. So the transmission probability is going to be equal to complex squared of that ratio, C to A. And big R, the reflection probability, is the complex magnitude squared of B over A. And then it should be true. The reflection plus the transmission should equal 1. It's got to work out. If it doesn't, you've done something wrong. I haven't proven it to you yet, but the Schrodinger equation conserves probability. We're going to look at that. That's coming. There's no way to get rid of members of the ensemble. They have to show up someplace. So if you have something like this, if this is violated, then you've not solved the Schrodinger equation correctly. So if we've solved it correctly, this should add up. Okay, so when we're looking for B and C, these two equations. B divided by A is the reflection, the fraction of those reflected by squared, complex squared. C over A complex squared will be the transmit probability. Is that closer to what you were looking for? I mean, that's what you were thinking. That's what you were thinking. I think that
Yes.
express itself mathematically.
Yes, but I'm still confused.
Well, okay. Can you help me out? Why are you confused?
I have no idea.
Does this make sense?
Yes.
Okay.
Maybe it helps to say basically A squared is equal to B squared plus C squared. So I think what she was originally thinking was like A is equal to B plus C.
A squared equals B.
So
Oh.
we got that equation right there on bracket side.
A squared. We can rewrite this. Let's put it this way. B squared plus C squared.
That helps.
Okay.
Thank you. Okay.
You see how to go from here to here from these definitions? Just multiply by the absolute value of A squared. Multiply this equation by A squared. That gives you this. So we're not, A and B are not A, B, and C are not probabilities, but they're amplitudes. That's the thing that you have to remember in this. The wave function is not itself a probability. probability amplitude. It's only psi star psi that is a probability.
It's kind of more of a broader scope question, but I was just thinking, so for the potential like VFX equations, is that, can we think of that just like as the defining scope for the problem?
Yeah,
Like that's kind of what's the boundaries that everything is falling under?
for a static, well, yes, that's right. So in other words, the Schrodinger equation is only going to give you something if there's a potential. So we're going to be taking different potentials and solving it for bound state problems or for scattering problems.
Okay. All right,
And so everything comes down to writing the Schrodinger equation and solving.
Yeah.
So we're just doing that for lots of cases to understand what is the nature of the solutions to the Schrodinger equation. But they all depend on the potential.
all right.
Okay, now remember also that what we did, this is a pure mode. So this is not the full solution if you have not a pure mode. This is only going to be reflection and transmission for a pure mode. If you have something that's mixed, a superposition, then it's more complicated than this. So these are going to depend on the energy. Mode coming in. They'll also depend on the mass, H bar, and V naught bar, the strength of the potential.
But just for saying like the energy and particle coming in, like those, like, how do I explain this? Like the graphs you showed in class where it's like the perfect, each one is fitting into like the box.
The pure, so the difference here with the scattering problem is that the energy is not confined to these certain values. Right? The energy is continuous. I can select any energy incoming electron that I like. Whereas for the bound state problem, the energies have to have certain particular values. Pure modes are only certain discrete values. So for the scattering problem, the energy is continuous, set by the experimenter outside. Correct. So there's the difference in the mathematical structure. In one case, we're looking for the discrete energies. In the other case, we're looking for coefficients as a function of the incoming energy. Different kind of problems, those two problems, bound state problems, and scattering problems, are different in their character. We always go to the Schrodinger equation though.